Hi guys, good afternoon. So this video today is showing my progress in trying to create some code to control a 74HC165 parallel in serial out shift register, and I'm doing so with the PIC16F684. And in preparation for this project, I already made a video on this particular shift register, basically just teaching myself how to manipulate it with debounced push buttons. And what I've done here in this code is I tried to copy exactly what I was doing with the push buttons controlling the shift register, but now I'm just doing it with the 16F684 microcontroller. And that's why in this code, which I will read through in a moment, I included all of these delay routines. Here's one here, here, all throughout testing of the bits I call delays. And that's just so I can visually test it on the breadboard, because once again the microcontroller can operate at 20 megahertz, and I won't be able to see what it's doing at that speed unless I put in delays to slow things down. So I won't recap much about how the shift register works. Please watch the links I have left below, which should bring you up to speed. And once again, thank you for watching. So I will read through this line by line. It's a little bit of a memorandum for myself, but thanks for watching. So here's just like the include files. I have it twice, probably not necessary. Here's the configuration bits, and I've set up some equates, which are just memory locations. These equates are used for the delay routine. They're just counters to be stored in these memory locations. But this C2, it's the memory location that I've designated so I can take the serial output data from the shift register and basically log it into the microcontroller, and I can store the 8 bits from the serial output of the shift register. I can store it in this file in the microcontroller. Unfortunately, looking at my breadboard setup, I have no way to test and see if this is actually working correctly and the value is getting correctly stored. So that's a work in progress to test to make sure that's working properly. But I can vouch that at this point I have got the pinouts, the GPIO pins on the microcontroller correctly manipulating the shift load pin on the shift register and the clock pin on the shift register and the serial out pin on the shift register. Okay, so I defined, these aren't bit masks, are they? Well, anyway, maybe they are. But I've assigned the pins that I'm using names, variable names, I suppose, and I've assigned them based upon the shift register pins that they are controlling. And I have 2 output pins, which is the shift load, which this output pin controls the shift load pin 1 on the shift register, and this clock pin on the microcontroller controls the clock pin on the shift register. This is the input pin on the microcontroller that will test the serial output of the shift register. Alright, I brought it up again just to make things more clear. So here is the shift register And the first step in using this is to send a signal in to the shift load pin. Of course, this is after you have your data pins hooked up. And you send a low signal into the shift load pin, and then you clock in or you clock out each serial data pin with the use of the clock pin. You also send that a logic low. And here's pin 9, which is hooked up to an LED here. But in my case, I'll have a microcontroller input pin obtaining the high and low data that's being put out on the serial output pin, which is pin 9 of the shift register. So maybe that makes this a little bit more clear. This is the shift load pin, the clock pin, and this is the serial output check pin, which is an input. And my code is started with the press of a push button. So once everything's set up on the breadboard, I want to check what the serial output is doing. I just push this push button. But this push button is just a plain old regular push button setup, and it's not hooked up to the shift register. So now I have the org directive, just starts things off, and it goes to the initialize label, and it just sets things up. In leading up to this video, I found I had problems because the comparators were not turned off. So I turned them off with this code. That's what that does. It's a wise thing to do, especially using port C without really explaining all of it. Turn the comparators off. From here on in, I'll probably end up including this code block to make sure things are working correctly. And now I'm bank switching to the bank where ANSL, the analog select settings, are located, the register, and I'm setting all the pins to digital for port C. And now I'm moving this value into the working register so I could set the TRIC register. And basically I'm making RC0 and RC1 of port C. I'm making those outputs, and then I'm making these next RC2 and RC3, I'm making those inputs. This one will be the serial output check for the shift register. And then I just return things back to bank 0, where most of the work is done in programming. So I mentioned up here in this equate that C2 is a value I specified to store an 8-bit value that I'm obtaining from the serial output of the shift register. So just to initialize things, I'm clearing it just to make sure that it's all zeros, it's empty. Okay, as I mentioned up here, I have 2 output pins. The shift load and the clock pin in their active state need to be set high, which is what's happening here at the end of this initialization setup. So the shift load pin and the clock pin are set high. Alright, so the whole code begins to iterate through if I push a push button, which I set up. And this checks if the button on port C, pin 3, is pressed. So this will just hang here. It'll bit test the file and skip if it's set. So it's going to wait, and then the next line does a go to, it says check button, it goes back up here, and it keeps iterating through this code until this input pin, which is I'm calling a push button check, till it goes high. Once it goes high, it breaks out of this routine. Slow things down a little bit with a delay. The delay is at the end of my code. It's there. I probably don't need to explain that one, the delay routine. So anyway, when the push button is pressed, little delay, then it goes into clearing the shift load on the shift register, because that pin is an active high. So when you set it low, it shifts the data on your data lines of the shift register. It shifts that data into the shift register when you send it low. So I bit clear the shift load pin, little delay, and then I set it high again. So then on the shift register, it should be automatically sending out the first bit of data, which is the most significant bit, and it's going to bit test that. So bit test file skip if clear. Now hypothetically, I don't know what the number is, but supposing the most significant bit is a 1, it will bit test the serial output, and it'll skip if it's clear. So let's just assume it's a 1, it won't skip it, so it'll go to the next line, which is call if ls, this should be an M. So if it's a high, it won't skip. It'll go to this next line of code, which is call, and it's a separate subroutine which I called if MSB is high. So then it'll go down to the subroutine here, and it'll move this binary value of 1 and zeros after it into this memory location, which I created and gave a name to, and then it'll return back here. It'll bit test that same serial output, and if it's set, which it still is, it'll skip if it's set. So it'll skip this next line if it's set, so it won't go through this routine, and then it'll proceed to the bit tester to clock in the rest of the 7 remaining bits. Now, hypothetically, the most significant bit could actually be a low or a 0, and in that case, instead of breaking into this subroutine, it'll go into this subroutine, and it will start by writing all zeros to the memory location C2. But really, the most critical thing is that it's sending a 0 bit to that C2 memory location, which once again I set up as an equate up here. But anyway, this is kind of a technical necessity that if you get experimenting and playing with the 74HC165 shift register, you'll realize that once you send the shift load low and then high again, it automatically spits out the first most significant bit on the serial output. So this is why I can't include this most significant bit in this subsequent bit tester routine, because it automatically spits it out. So I had to deal with it in this. I had to deal with it first before I get into bit testing each subsequent bit of the serial output line of the shift register. Okay, I guess a word I'm thinking of is redundant, because here's my bit tester routine, and I basically have the same code copied and pasted, and as I'm testing each bit. So the first block here, I'll be testing bit 6. And the reason it's bit 6 and not 7 is if you look at a bit and if you look at a byte, and you look at the least significant bit, the least significant bit is called bit 0. So that bit 0 is the first bit, which is why it might seem a little confusing, but if you think that one through a little bit, you realize that bit 6 here is just the next bit to the right of the most significant bit. So already we've kind of dealt with the most significant bit up here, and so now we just need to deal with the next bit, which is actually bit 6 if you stop and think about it. And yeah, I guess I'll read through the first one. So it'll call the clock routine, which comes down here, which bit clears the clock bit, then it delays, and then it bit sets the clock bit. It's like a push button press here. It's like pushing the button and then letting go, which will advance the next bit being clocked out of the serial output of pin 9 of the shift register. So this clocking, or this almost like a finger press of a push button, I made it a separate subroutine. So I just call it each time. So when we call it, then we can bit test what's on the serial output. And this is the input pin of the microcontroller hooked up to the serial output pin of the shift register. So we're going to test that, bit test the file, skip if clear. Now again, this is hypothetical. We don't know if this is 1 or 0, but let's assume it's a 1. So it'll bit test if it's clear, bit test file, skip if clear. It's not clear, it's set, so it won't skip anything. It'll go to the next line of code, and it will bit set F in that memory location I defined, I called C2, and it'll take that information and it will store it in bit 6 of this C2 equate I created. And then it'll bit test the file and skip if set. I think we were assuming that it was set. So it will skip over this next line of code, and it'll call another delay to slow things down, and so on and so forth. And it does this for bit 5, 4, 3, 2, 1, and 0. Are there ways to optimize this code so that I don't have to write everything out each time in a rather similar fashion? Absolutely there is, and that's a work in progress, but I just need to test and see if this is working properly before I start optimizing the code to clean it up. I look forward to doing that. So I already discussed the clock routine, and I'm not really going to try and explain the delay routine. So now the question is, how do I test the data in this C2 equate file by the end of the code to make sure that it worked properly? How do I do that? I'm thinking about using the other type of shift register, which is the serial in parallel out. And there's enough pins on this microcontroller to use both shift registers, and then I can actually see if it's working correctly. So this is sort of like not a final video of this project, but at least it's the part of the project where hopefully I've gotten the 74HC165 shift register.
Hi guys, good afternoon. Allow me to explain. I've even confused myself in everything that's going on. So anyway, I have my PIC16F684 chip, and I'm trying to control an 74HC165 parallel to serial shift register. It requires 8 bits of data on the data pins, and I'm supplying it with this counter I built. So this is just some random data. Most significant bit is a high, low, high, high, low, high, low, high. And this shift register, the 74HC165, is ultimately controlled with 3 pins. The shift load, which is pin 1, the clock pin, which is pin 2, and the serial out, which is pin 9. I'd love to explain more about that, but there should be some links below which show the follow-up or show the preceding videos to this one, explaining how I got this chip working manually. And now what I've done here is, instead of using debounced switches that you press with your finger, I've got the microcontroller doing that instead. So I got rid of my multi-switched debounced switch module, and now the microcontroller, I've written a program for it, and it should be doing the work. So everything is started initially in the code with the press of a push button, and this is an input pin, and when it goes high, it cycles through a signal to the shift load pin, which is pin 1 on the shift register, and the shift register will then clock out each bit of data on the clock pin, and the microcontroller initially sends a shift load signal. It sends it a low, and then it clocks the clock pin 8 times. Now I put delay routines into the code because the microcontroller can iterate through code at 20 megahertz, which is way faster than the human eye. So I slowed it down to mimic almost like the finger press of push buttons from a human. So I put lots of delay routines to slow things down so I can see how it works. But one of the things that I can't see is that on the output of the shift register, there's the serial out pin. Well, you can't see that. There it is. And based upon the serial out pin, the microcontroller is taking in an input on one of its input pins, and it's logging the 8 bits, the highs and lows on the serial output, and it's logging that into a memory location which I defined at the beginning of the code. The trouble is the logging in of all the 8 bits of data from the serial out pin of the shift register can't really be seen on the breadboard setup. Nor do I have a great way of checking to see that the microcontroller is doing its job by accurately logging in that value. The PIC16F684 does have limited pins. It only has 12 pins. There probably is a way to do it. Unfortunately, each of the ports don't have 8 GPIO pins each. So that's another trick. So what I was actually thinking of doing is having a different type of shift register, the serial in parallel out shift register, also spit the data back out. That's a work in progress. So anyway, that's a lot of talking to introduce this. So here's everything starts with the push button press. This gives it a high. and then it'll send the shift load, which is blue. It'll send that low, and then it'll clock the clock pin, which is green, the green line here. It'll clock that 7 more times. So you might see the push button press. It's hooked up to the orange pin. So I'll press it. You should see it go orange here. And based upon the counter value, it actually matches up with the serial output value as well. It should go high, low, high, high, low, high, low, high. I'll demonstrate it a couple more times.